Hey, what's up, pre-calculus? We're going to talk about some vertical transformations of creature functions today. Just little functions that I've kind of dreamt up for you that don't really have a specific equation they're based on, but just, a couple sampling of x and y values. So the featured function values for each example are shown in the middle box of values here, and throughout this video we are going to try some transformations of these equations and see what they look like on a graph. So here we have it, a sampling of these 6 points placed together on the graph and connected, and we are going to examine 2 transformations of them. We're going to examine what the equation g of x looks like. The rule for g is that we take the function f of x and add 2. Well, let's think about how that math would look. Let's think first of g of negative 4. All right, the rule implies we should place the negative 4 in for the x, and now when we go to compute f of negative 4, let's look at our chart. F of negative 4 is 0. And I look that up, write in the 0, add the 2, and that comes out to 2. So let's put that in the chart there. And as we kind of think about what just happened, the real rule that's being added here is that to go from the original y values to the new y values, to each one of them we should add a value of 2. So let's make that happen together. 3 plus 2 becomes 5. 0 plus 2 becomes 2. Negative 2 plus 2 becomes 0. And 0 plus 2 becomes 2. And great, we have a whole new list of ordered pairs. How about we plot them now? Negative 4, negative 2. Negative 2, 5. 0, 2. 2, 0. And 4, 2. Beautiful. As we reconnect these points along the function, we get the graph of g of x, which I've tried in blue. Okay, I would like for you guys to pause the video and see what you can do with the new function over here, h of x equals f of x minus 2. Welcome back here. I'm going to uncover my work here. I did do it in a different color just to set it apart from the original. And the new function, notice all of the y values became lowered or decreased by 2. And clearly, analyzing the trend here, we see the blue graph has moved up by 2, the red graph has moved down by 2 based on the original, and we can call something like this phenomena vertical slides. You're simply sliding the function graph up or down by a specific value. We do refer to this as a rigid transformation simply because the shape itself did not change. You see that same exact shape 3 times in a row. They're just located in different places. So let's look at another vertical transformation. In this case, we're going to do a reflection. Okay, so just like in the first example here, we've got a couple sample y values that are placed here on the graph. I'm just going to highlight them. And I'd like us to examine what happens when we make a new function g of x, which is the opposite of the function f of x. So for example, g of negative 3, we would compute as the opposite of whatever f of negative 3 is. All right, well, the opposite of f of negative 3 is the opposite of 2, and so we get a y value here of negative 2. I think we can pretty reasonably see that what's happening here in this equation as we follow this rule is that the y values of the original function points are all changing signs here. The x values stay the same, the y values are switching. So I'm going to just quickly fill in these couple graphs here. Graph these points. -3, -2, -2, -4. 0, 0 didn't change. 2, 2. And lastly, 4, 2. And we connect the graph here. We connect the points. And we see, again, an example of a rigid transformation. It is the same shape. It has just been reflected over the x-axis. I'm just going to jot that up here. And that result hopefully does not shock you very much at all. Let's try one more vertical transformation of this little creature graph. We're going to take these same starting values as the first point and show them back on the graph again. We're going to examine some dilations. Now you'll notice I called this a non-rigid transformation, and we can perhaps anticipate the shape itself might be a little distorted as we regraph according to these two new rules here. So let's think about how the y values of this function g of x would change from the original function f of x. We're going to, well, maybe I'll try it for a value of -4. So the rule says take the number 2, multiply it by f of -4. Now in this case, that's not a very exciting multiplication. It comes out to the same value, but I do kind of think can still get the essence here that in order to perform this transformation, we will take all of the y values from the original graph and multiply them all by 2. So if I fill in my little handy chart here with these new y values, gives me a chance now to see what the graph of this function looks like. And I do quickly see a new shape forming. It is still the same width. There's been no change to the x values there, but now the shape is twice as tall. Okay, so I'd like you to try to apply that same idea and see if you can graph that function h of x. Maybe try it in a different color so you can keep it straight, and I'll pause the video, let you catch up. Everybody, welcome back. Let's see how that graph took shape. Hopefully you certainly have noticed, again, as we multiply these values outside of the function, they do affect the y values of the graph. The x values stay the same. So for my new rule here, h of x equals 1/2 times f of x, all of the original y values did get multiplied by 1/2, showing them on the grid. I can now see the new shape is half as tall as the old shape. So the best way to describe these two transformations are to say in what direction the graph changed, vertical or horizontal. In this case, vertical. Taller and shorter are vertical issues. You want to say if they got bigger or smaller, so expansion and compression can describe that for us. And then you want to add one more level of description here and say by how much the graph got bigger. Well, it got bigger because it's twice as tall. So vertical expansion of 2, or it got smaller, and how small did it get? Well, it got half as tall as it used to be, vertical compression of half. I'd like you to flip to page 3 now in your notes. And I'd like us to just fill in a couple of the rules that we just saw. So certainly everything here in the first column is a vertical transformation. And we'll come to see all of those transformations live outside of the function, whether we're talking about a specific equation or the function notation f of x itself. And so what we saw, adding and subtracting values, move it up or down. Negative multiplied to the function reflects it over the x-axis. And think back to what we saw before when we multiplied outside by a number bigger than 1, like 2, the graph grew it by exactly that factor, so we say vertical expansion of whatever that value is. And when we multiplied by a 1/2 on the outside, and really any other number between 0 and 1, that would have made the graph shorter by still a value of c. Again, if c is a smaller value, it makes the graph shorter. We will cover horizontal transformations together or in another video, whatever the case may be. Ta-ta!